exercise 731 is not asking us to draw the mechanisms for reactions. It's just asking us to predict the products. So if we were chefs and we went into a kitchen and we mixed this stuff together, what is going to pop out of that mixture? What are we going to get when we cook that? And that's all we want to find out. We don't have to think about the every step, the curved arrows of the mechanism here in this problem. So really, we know that all of these are either going to be an SN1 or SN2 reaction. So they're all going to be substitution reactions. So we're going to be replacing the leaving group with the nucleophile in every single one of these. So when will you get a different product for SN2 versus SN1 reactions? You will always get a different product if you have a chiral center. If your leaving group is on a chiral center, SN2 will only give you inversion of configuration. And SN1 will give you a racemic mixture. In other words, if you have a chiral center and you do an SN2 reaction, you will only get one product. The product will have the nucleophile attacking on the opposite side as the leaving group left on. But if you do an SN1 reaction with a chiral center, you will get two products, each of the enantiomers at the chiral center. So that's one thing to watch out for. The other thing to watch out for is that with SN1 reactions, you have those carbocation rearrangements, and that can change the carbon skeleton, and it can change where the nucleophile attacks. So those are serious changes to your product, so watch out for that. Otherwise, those are the only differences between the product you would get between an SN1 and SN2 mechanism. Okay, so with that in mind, with those in the back of our mind, let's try to predict our products. First thing is to identify the leaving group. So that's what's going to go away. Now let's identify the nucleophile. That's going to take its place. Okay, do we have to worry about... First of all, we don't have a chiral center here. Notice that this atom that's on the leaving group, if you go there, you go around, you hit the same things at the same point as if you go around the other way. So those two branches are really the same, and so that's not a chiral center. So we don't have to worry about drawing one product for SN2 with inversion of configuration, or two products for SN1 as a racemic mixture. We don't have to worry about that. Do we have to worry about carbocation rearrangement? Well, that's a little interesting. This is definitely going to happen through an SN1 mechanism, because the leaving group is on a tertiary carbon. This carbon is bonded to 1, 2, 3 other carbons. So that's definitely going to be an SN1 mechanism. And if it doesn't make sense to you why I'm saying that, go back to the previous videos, the last few videos where we've learned how to decide whether a mechanism will be SN2 or SN1. So this is definitely SN1, but what type of carbocation do we get? If the leaving group leaves, we end up with a positive charge where it was. That's a tertiary carbocation. If you go up, it would be primary. If you go to the left, it would be secondary. If you go to the right, it would be secondary. It is at the most stable place it could be. So you won't have a carbocation rearrangement. Well, that's convenient. All we have to do is replace the leaving group with the nucleophile. So we'll redraw the carbon skeleton. Now notice our nucleophile here has no full charge. It does not have a full negative charge. Remember, the Me stands for a methyl group. That's CH3. So this is completely covalent. There's no full negative charge. So when this molecule attacks, there's going to be a last step where you have a proton transfer. You're going to end up taking that hydrogen off. So you'll only be left with OMe. And that's it. That's the product. All right, let's get some more practice, build some confidence with this. So we look at the substrate. We have the leaving group on a secondary carbon. So right now, it's not clear necessarily whether this is SN1 or SN2. We have a strong nucleophile, and a polar aprotic solvent. Both of those things convince us that this is going to be an SN2 reaction. And again, if you are not confident on how to tell, how to use the nucleophile and the solvent, and the substrate to tell whether you have an SN1 or SN2 reaction, I strongly encourage you to go view those older videos where we spent a lot of time building up that skill. So this is going to be an SN2 mechanism. So if we had a chiral center, it would be inverted, but we don't. Going around clockwise, this ring is the same as going around counterclockwise. You run into the same stuff at the same point. And so we don't have a chiral center, so we don't have to worry about inversion of configuration. And we don't have to worry about a carbocation rearranging. So all we have to do is draw that same carbon skeleton, but replace the leaving group with the nucleophile. And that's your product. Okay, let's figure out the mechanism for this one. We have a leaving group. It's a bad leaving group, but that's okay. We can do a proton transfer, turn it into a better one. The leaving group is on a tertiary carbon. This carbon is bonded to 1, 2, 3 other carbons. And so because that's on a tertiary carbon, we know immediately this is going to be an SN1 reaction. With SN1 reactions, we have to worry about two things. First, if we have a chiral center, we have to worry about drawing two products, each of the enantiomers. And second, if it's SN1, we have to worry about carbocation rearrangements. So first, let's think about carbocation rearrangements. If the leaving group leaves, and we're left with a positive charge here, that carbocation is tertiary. This carbon is bonded to 1, 2, 3 other carbons. Oops. To the right, it would be secondary. To the left, it would be secondary. To the top, it would be primary. None of the other positions would give a more stable carbocation. So the carbocation does not rearrange. It stays on the tertiary carbon. So we don't have to worry about carbocation rearrangements. Okay. But we do have a chiral center. To the left, we have a propyl group. Above, we have a methyl group. To the right, we have an ethyl group, and then we have this OH. So this carbon here, where we're doing this reaction, that is a chiral center, which means that we'll get a trigonal planar, a flat intermediate, carbocation intermediate, and the nucleophile can attack both on the top and on the bottom of that, and that will give two products. Oops. So the first product, the nucleophile, which is just this bromine, right? The hydrogen is stolen in the first step to turn the OH into a good leaving group. The bromine comes back later to attack as the nucleophile. So just the bromine, that will go on this carbon, the same carbon as the leaving group, because that's where the carbocation will be. But in one case, it will attack the top of the flat pancake carbocation, and in the other case, it will attack the bottom. And so you get those two enantiomers. You get two products. So remember, if you have an SN2 product, if you have an SN2 mechanism with a chiral center, you only get one product, the inverted product. The nucleophile would attack on the opposite side that the leaving group left. And if you have an SN1 reaction with a chiral center, you get a racemic mixture, 50-50 mixture of each enantiomer. Okay, so we have those two products. All right, let's think about D. We have a good leaving group, this OTS. We've seen that's a tosylate group. You can see what that looks like at the very end. You have these awesome leaving groups here, and the tosylate group is an awesome leaving group because it can take a negative charge and stabilize it through resonance, really over a huge number of atoms. So that OTS is a tosylate group. It's a good leaving group. So here we have a good leaving group on a primary carbon. This carbon is only bonded to one other carbon. Well, so immediately it's primary, we know it's SN2. And in case we were uncertain, we have a strong nucleophile in a polar aprotic solvent. So definitely SN2. Well, this isn't a chiral center, so we don't have to worry about inversion of configuration. All we have to do is draw the replacement of the leaving group. We have to replace that with the nucleophile, which is just the CN. Notice the sodium is a metal. It's going to give its electrons away. This CN will take them. So the CN is the nucleophile. So we replace the leaving group with that nucleophile, and that's our only product. So hopefully you're seeing that you kind of have to know everything in the whole chapter to do these. But if you know everything in the whole chapter, they don't take that long, because you don't have to draw everything out. If you're ever in doubt, though, you can draw everything out. Okay, so here there is a typo. This should have an iodine here. So if in your packet you don't have something there, you would write the iodine in there. And so you have an awesome leaving group. That leaving group is on a tertiary carbon. So this is a tertiary carbon. That means that when the leaving group leaves, you'll have a tertiary carbocation. Oops. When the leaving group leaves, you end up with a tertiary carbocation. And that carbocation is more stable than any other position. Sort of to the top right, it's secondary. Here, it's primary. If you go to the ring, it's still tertiary, but that's not any more stable. And it would take energy to move a hydrogen from that other carbon to get the carbocation to rearrange. So there's no driving force to make that movement. So there's no carbocation here. I mean, there's no carbocation rearrangement here. So we don't have to worry about that. We do, however, have a chiral center, because this carbon is bonded to 4 different things. It's bonded to an ethyl group, to a methyl group, to an iodine, and to a cyclohexyl group. So it is a chiral center, and if you ever have a chiral center with an SN1 reaction, you end up getting 2 products. Because you form that flat as a pancake carbocation intermediate, the nucleophile can attack on either side, so you end up getting 2 products. So one product will have the nucleophile, and notice this nucleophile has no full negative charge, so there's going to be a proton transfer at the end of the mechanism, and it'll just end up being an OH. So in one case, the chiral center will be the same as in the original molecule. You're just replacing the leaving group with the nucleophile. But in the other case, you'll have the other enantiomer. The ethyl group will be going away, and the methyl group will be coming out at you. So notice these are opposite hands. If this is right-handed, then this will be left-handed. So those are the 2 enantiomers. You get both enantiomers when you do an SN1 reaction. So this does require you to have mastered the SN1 mechanism, to know what I'm talking about when I say you won't get a carbocation rearrangement because this has no full negative charge. There will be a proton transfer at the end, so it's only going to be OH. If those words don't make sense to you, go back to the videos that walk through the mechanism of an SN1 reaction and master that before you go to this problem. So we have that SN1 with a chiral center, so we had a racemic mixture of 2 products. Okay, last one. Here we have a leaving group on a secondary carbon. This carbon is bonded to 2 other carbons. The leaving group's on a secondary carbon, so this is a toss-up right now. It could either be SN1 or SN2. We look here, we see a metal. That means that this is really an ionic bond. You have sodium with a positive charge, Cn with a negative charge. A negative charge on a small atom, that's a strong nucleophile. So that's starting to look like it may be an SN2 mechanism. Look at the solvent, dimethyl sulfoxide. That's a polar aprotic solvent. Both of those favor SN2 reactions. Strong nucleophiles and polar aprotic solvents favor SN2 reactions. And you can see that in the little summary that we had last time that we've been using in these problems. Strong nucleophiles and polar aprotic solvents favor SN2 reactions. So this is definitely going to happen through an SN2 mechanism. Now, in a sense, that's nice. We don't have to worry about carbocation rearrangements. But we do have a chiral center here. Notice that we have a methyl group, we have a bromine, we have a cyclohexyl group. Oops. And the fourth thing is a hydrogen, which would be going away. So we do have 4 groups. So this carbon here is a chiral center. And when you do an SN2 reaction with a chiral center, you only get one product, but it's the inversion product. So we're only going to get one product, but it will be the product that gets inversion of configuration. In other words, if it kept the configuration that it has, then this methyl group would be coming out at us, and we would just replace the bad leaving group, the bromine, or I'm sorry, we'd replace the leaving group, the bromine, with the nucleophile, the CN. But that would keep the configuration. We need inversion of configuration, so we take the stereochemistry we have and we flip it. So the methyl group, instead of coming out at us, would be going away. And that's inversion of configuration. And notice you only have one product here for this SN2 reaction. So in this exercise, we were really using all of the careful thinking that we built up through this whole chapter to do a quick analysis to predict what we would make when we mix different substrates with different nucleophiles.